This video is all about inverse functions. If I have the function y equals 4 times x, then its inverse function would be y equals x divided by 4, because dividing by 4 is the inverse of multiplying by 4. If I had a function y equals x plus 1, then its inverse would be y equals x minus 1, because subtracting 1 is the inverse of adding 1. If I had the function y equals e to the power x, then its inverse function would be y equals ln x, because ln x is the inverse of e to the power x. More generally, if I have a function y equals f of x, then I say that its inverse function is y equals f minus 1 of x. That's not a power, that's just the notation of writing inverse function, f minus 1 of x. Now, the whole idea of the inverse function is it undoes the original function. So timesing by 4, then dividing by 4 will take you back to the number you started with. Adding 1, then subtracting 1 will take you back to the number that you started with. Doing e to the power of a number and then doing ln of that number will take you back to the number you started with. So doing f inverse to the f function will just give you the x value you started with. So that's the idea of an inverse function. Let's talk about that a little bit more. An inverse function serves to undo the original function, to get you back to what you started with. The output becomes the input, is another way of saying that. What I am basically saying here is I'm swapping the x and the y. The output becomes the input. The x and the y swap. So, if I had a function, getting a bit more complicated now, a function h of x equals e to the power x plus 1, where x can be any real number. So that's the domain of the original function. I want to find the inverse function, and I want to state what the inverse's function domain and range is. Well, first thing to state, I already know what the inverse's function range is. I know that its y can be any real number. And I know that because I've just copied it from here. Because like I said a moment ago, the range and the domain flip. They swap. The x becomes the y becomes the x. That's the idea of the inverse function. So, if the domain of the original function was x is any real number, then that means that the range of the inverse function can be y is any real number. So that then gets me thinking about, well, what's the domain of the inverse function? That should match up with whatever the range of the original function was. So what is the range of e to the power x plus 1? Well, we've seen previously how we can work out the range. Let's just do this quickly. We'll draw a quick graph. So I know that e to the power x looks like this, going through 1 there with an asymptote at y equals 0. I've got a plus 1, however, so that's going to move this graph up 1 square in the y direction. So actually, my new asymptote is going to be at y equals 1. It's going to intersect on the y-axis at 2, and it's going to look something like this. So from that graph, I can say that y is always greater than 1. It has to be bigger than 1. Can't equal 1 because of the asymptote. So y is greater than 1. That's the range of the original function. Which then that means that's going to be the domain of the inverse function. So I can say for the inverse function x has to be greater than 1. So I know the domain and the range of the inverse function, but what is the inverse function? What is the inverse of y equals e to the power x plus 1? Well, remember what I said. The inverse function flips the range and the domain, the x and the y. So the x and the y are going to flip around. And now I'm going to rearrange this to make y the subject. Excuse me. So subtract the 1 from both sides. And now I'm going to take logarithms of both sides. So there, I could say that y equals ln x minus 1. Or in its usual notation that I would give for this, for the inverse function, I'd say h inverse of x is equal to ln x minus 1. This is the inverse function of this with its domain and range. Now, before we move on from this, let me just show you what this looks like graphically. And then we'll look at another example. So in black here, we've got the e to the power x plus 1. And in red here, we have the ln of x minus 1. And I hope that you can spot something. If you can't, hopefully you can see now by me putting this dotted line in, or this mirror line in. This is the mirror line y equals x. I hope that you can see that they are reflections of one another. The inverse function is a reflection in the line y equals x. Which should actually hopefully make sense, because remember what we said. The y values become the x values. It's been reflected. This has been reflected down to be there. The range became the domain. And similarly, the x values here have been reflected to be the y values there. The domain became the range. And that's always going to be the case. Let's have a look at another example. Here we've got h of x is equal to a half x squared minus 1, where x is greater than or equal to 0. I need to find h inverse of x, stating its domain and its range. Well, straight away I can write down its range. I can just copy this from the domain. If x has to be greater than or equal to 0 in the original function, then y has to be greater than or equal to 0 in the range of the inverse function. Just copying it directly from there, because I know that the x and the y flip. Next, the domain. I know that the domain is going to match up with the range of the original function, which I can find quite easily. Now again, let me just draw a quick sketch. It's just a nice simple quadratic. Oops. There we go. So my quadratic, it's cut through at minus 1 here, and would look something like this. I'm going to draw the quadratic like this for now, and then I'll talk about why actually that bit shouldn't be there in a minute. So the range of this, looking at the y values, I can see that y has to be greater than or equal to minus 1. It can't be less than minus 1. It can be anything above minus 1 or equal to it. So the range of the original function was y is greater than or equal to minus 1. So therefore the domain of the inverse function will be x is greater than or equal to minus 1. Right, let's now find the actual inverse function. So again, I'm going to write down the function y equals half x squared minus 1. The x and the y flip, because that's what the inverse function does. And I'm now going to rearrange to make the y the subject. So add 1 to both sides, multiply both sides by 2, and then square root. Now to write this in its usual form, h inverse of x is equal to the square root of 2x plus 2. This is my inverse function, this is its domain, this is its range. Again, let's look at what that looks like graphically. So I've got both of those plotted on here. In blue, we've got the quadratic, and in green, we've got the square root, the inverse function. Now, notice that the green function, the inverse function, doesn't continue going down. Well, that's drawn really badly. Doesn't keep going down here like that. That part of the graph is not being shown. And the reason for that is because if it was, it wouldn't be a function. Remember that the definition of a function means that for every input there has to be one unique output. Here there would be 2 outputs. It wouldn't be unique. That breaks the rule of what being a function is. So that part of the graph is not shown there. So therefore, this other part of the graph should also not exist as well. This part over here should not be there, because otherwise that would be reflected. That should not be there. And that is why there was that original domain restriction there, where we said that x had to be greater than or equal to 0. It had to be there like that. We were only looking at where x is positive values. We can't be looking at these negative values there. Now, when we look at that function itself there is nothing to stop that original graph by itself being there. It's still a function. That blue line is still a function. For every one value of x, we get a unique value of y. That's fine, that is a function. It is a one to many, a many to one function. Many inputs, one output. That is fine, that's a function. But the problem with that is that when you take the inverse of that function, that many to one, because remember, the x and the y flip, the many to one suddenly becomes a one to many, which is not a function. So in order for a function to have an inverse, it has to be one to one. It has to be one to one. If it's not one to one, then its inverse won't be a function. So what we had to do in this case was we had to give that domain restriction at the beginning, so that it was a one-to-one function, so that the inverse function would be a function. The idea of the reflection, the line y equals x, still holds true. Hopefully you can see this. This is my line y equals x, and hopefully you can see that the green line there is a reflection of the blue line in the line y equals x. one last thing for this video. Based on what we just said about the reflection trick, I don't actually need to know the function to be able to draw its inverse. So I've got the function y equals f of x there in blue. I can draw the line y equals f inverse of x by just taking its reflection in the line y equals x. So if this is y equals x, let's reflect the blue line in that line. So it's going to look something like this. Going through there. So that would be my inverse function. One final trick. If we are asked to solve an equation, f of x equals the f inverse of x, there is a trick we can use, because that tends to be quite complicated to solve. Certainly a lot of algebra involved. But the trick we're going to use is the fact that, let's have a look, when does our function equal its inverse function? Well, they are equal to each other here, here, here. In fact, they'll only be equal to one another. They will only intersect on the line when y equals x. So where they intersect, they also intersect with the line y equals x. Which is useful, because that means rather than solving this equation, I could just solve the equation f of x equals x, because the f function also intersects with the x function at that point, at that point, at that point. Or if it was easier, I could solve that f inverse equals x. They will all have the same answers because they all intersect with one another at those points. So just in that one special case, if we were asked to find where the function equals its inverse, we could just take the function and make it equal to x instead and solve that. So that's inverse functions. That's how we find them. That's how we find their range and domain and what they look like graphically.